Hi, my name is Ken Peters. I'm with the Jet Propulsion Laboratory, and government sponsorship is acknowledged for this work. And this work is what I call embedded Gcov, which is a way to get the GCC Gcov code coverage data extracted from an actual embedded system without requiring a file system or even an operating system or standard C libraries. And the benefit of this is that in the past, I have usually had to get code coverage information by compiling a version of my embedded code for Linux, where I can run it and get code coverage data there, or create some sort of Linux imitation of my embedded system that I can run on, but then that model may not be accurate or include all the aspects of the hardware. So being able to extract the coverage data from the actual embedded system is a big advantage in my mind. For those who are not fully familiar with Gcov, a quick overview. Basically, you compile your code with GCC options for coverage tracking. And I'll repeat, this does assume that you're using GCC compiler tools, or at least GCC-based tools. There are some others that support the Gcov format, but primarily this is aimed at GCC. So you provide the arguments F-test coverage and F-profile arcs in order to enable code coverage for the source code files that you want. You don't have to compile every source file for coverage. You might not want to if you have to fit the resulting image into a PROM or some such where you don't have a lot of space, and so you may have to pick and choose files to cover. When you do compile it with the source coverage, the GCC inserts counting code around your function calls and branches. As a result, the program timing is slowed and your image file size is increased. So you probably want to do the coverage as a separate build that you use to run your test scripts or other test routines and see what code was hit and what code was not hit by your tests. Then you improve your tests, you hit more code, and continue that until you're ready to run for the record. Then you would do a build without code coverage, run your test routines on that, and you would have confidence that your test routines are now covering as much of your code as they reasonably can. So you run the program with coverage, you extract the coverage counter data from your program. When you ordinarily use Gcov in a Linux system, the output is a bunch of separate data files, one for each source code file that you compiled for coverage. An embedded program may not be able to write files like that, and so this talk covers another way to get your data out. Once you've got the data out, you can run Gcov to decode the coverage data and produce annotated copies of your source files that show what code's been executed and what code has not. Or there are other tools available besides Gcov itself that can provide more graphical displays of the data that you may prefer. Here's an example of the Gcov output. This comes from Wikipedia. There's a little bit of source code, and it shows you how many times each line of code has been executed. And here with the hashtags is a line that was never executed. And as I mentioned, there are other tools that can process this into more interactive HTML or other forms that are easier to present or easier to drill down and understand. Icov is one such tool that's freely available. Another tool is coveralls that lets you upload data to a coverall server, and then you can look at it. How does this happen inside the code? On the left, there's an example of a Hello World program compiled without code coverage. On the right is a object dump compiled with code coverage, and you can see that there's additional functions Gcov related that have been added by the compilation for code coverage. And for the embedded Gcov, basically what we're going to do is provide our own versions based on these Gcov functions provided by GCC that will emit the data instead of as a bunch of separate files in a file system in a simpler way that works for our embedded system. Though, of course, if you have the luxury of an embedded file system, you can use that. These Gcov files, there are two types of files. The GCNO files, notes files, are generated at compile time, and they contain information about the structure of your source code. The GCDA data files are generated at runtime and contain the counter information from the execution. So we need to get the GCDA data file information out of the embedded system. And that is what the embedded Gcov is going to do. This is not something that I created from scratch. This is based on publicly available preceding work. First of all, of course, there are the many GCC developers who created the Gcov data system. Then there are a couple of people who described how to basically do this online earlier. Thanasis Tsiodras at thanasis.space/coverage.html described the basic mechanism for doing this. And earlier, Alexander Tarasikov at allsoftwaresucks.blogspot.com, you can see the full link in the presentation, also described how to do this basically. And the two of those had different aspects of what was needed to be done. And I found that, at least in my system, there was additional work that had to be done to make this operate smoothly, especially if your executable has to be small, such as in PROM, but also if you wanted to have more flexibility and make this a little bit more portable and flexible and easy to use. So that is what I have done to expand upon what people had done before. So in order for the embedded Gcov to work, you have to insert 2 or 3 lines into your own source code. First of all, you have to include Gcov public.h. I'll talk a little bit more about what's in that header file later. You also have to include _Gcov_exit. That's the function that actually emits the coverage data so that you can extract it and get it at the end of your run. So in my particular system, I put a command where I type 9 and it emits the coverage data. In your system, you might want to insert that in a command, or you may want to insert it when your software exits, or do it periodically or something, depending on what suits your needs. You may also have to add a call to this Gcov call constructors function. That depends on your system's startup code. In a Linux system with running Gcov, this constructors are generally called automatically under the hood for you. And also this Gcov exit is called automatically when your Linux routine exits. But for an embedded system, depending on your startup code, you may have to do this Gcov call constructors early in your code. In order for those to work, you also have to add these source files to your build, Gcov public.c, which is basically the interfaces and so on, and Gcov_GCC, which is some of the more underhood things that attach it to GCC itself. Most likely you want a separate Gcov build target that puts these files in and uses the preprocessor flags to enable the coverage. You may also need a separate linker file. If you have to include the call constructors function, then it may need some helper symbols, and I'll talk more about that at the end. Once you've done this, then you compile with GCC and the usual code coverage flags to get an image that you can load into your system however you ordinarily do that, and then execute. Now, there needs to be some customization to work for your system, and most of that is done in the Gcov public.h file. It contains preprocessor definitions for a variety of features, and you would uncomment the ones that you need. Some of the major features are selecting which kind of output format you want. You can select a serial hexdump, or you can select a binary block of data in memory, or you can also select output to a file if you have a file system. There are other options to control whether you take advantage of other features your embedded system may or may not have, such as whether you want to use malloc in your system, or whether you have standard C library functions such as exit. So there's a variety of options, and the Gcov public.h describes those with comments that hopefully would make it clear which ones you want to select. There are also preprocessor definitions to abstract certain necessary functions so that you can adjust those if you need to in your system. For instance, there's a function to print a string, there's a function to print a number. You may have the ordinary functions such as puts for a string or printf for a number. In my system, I did have a puts function, but that was custom, and we had a custom print num function. So I use those as the definitions. The definitions that you need may be different. But if you have the ordinary standard IO library, then those definitions are available and you can select those. You might need to do some editing of the Gcov public.c file, depending on what features you're using. For instance, if you're not using malloc and you are using the binary memory dump, then you need to adjust the Gcov public.c to state the memory address where you want the information to be stored. Or you may have to change some of the print statements if your system doesn't support things that will go along with these Gcov print stir and Gcov print num macros. If there's like no way for you to accomplish those macros in your system, then you may have to adjust the C code to print things out in a different way that does work for your system, if you're using the serial hexdump. So once you then have compiled the system with its adaptations and run it and done the extraction by calling the Gcov exit function in whatever way you built it into your system, then the output looks basically like this, which is a concatenation of the GCDA data files for the different source code files that you compiled for coverage. So you can see here that it emits some data for jump.gcda, and here's the hex data. Similarly for sleep reset.gcda and autoboot.gcda, and there's a lot of other functions that were in between there. Then at the end of the dump, it says Gcov end, so that you know it did in fact print out all of the information it was supposed to. If you selected the binary memory output or binary file output, it's basically the same data in binary form instead of an ASCII hexdump. And you can extract that however your system allows, be it a debugger or a spacecraft interface that lets you get data out of your system. So this is able to be extracted even if you have no RTOS, even if you have a system that's so small that you just burn everything into a PROM. I extracted this data from the PROM boot code that's just bare C code running directly on the CPU. And you can still extract coverage data from that. Once you extract the coverage data, then you do post-processing on it to view it. Since ordinarily in Linux systems, Gcov expects a bunch of separate GCDA data files for each source code file that you compiled for coverage, we have to separate this concatenated output into a bunch of separate files. I use a shell script that calls an awk script on the serial port log file to do that. I haven't produced a tool for binary memory dump or binary files, but that would be pretty easy to do. So once I've got it split up, and then I can process everything the same way as I would in an ordinary Linux Gcov run. Nothing is different at this stage now that I've gotten the data out and split it up into separate files. So I myself use the Icov tool and GenHTML that comes with the Icov tool in order to get HTML output that I can display and drill down into to see what's going on. I have also pushed the results to a coveralls server at JPL with help from James Mertz and Michael Vanover. That does work. I haven't exercised it a whole lot, but I may use that more going forward. The next two slides, which are not quite the final two slides, but the next two slides show some Icov HTML output. And then after that, I'll talk about where this embedded Gcov is available. And then there are some backup slides that I can cover in the last couple of minutes. So here's some example Icov output. And it has a list of the source files I compiled for coverage, and shows the percentage of lines that were hit by this execution run and the percentage of functions that had been executed. And this was not a particularly exciting coverage run. I just typed in some commands and then dumped the coverage out, but it gives you the idea of what Icov displays look like. And if you click on one of these file links, then you get a listing of that source code file, and it shows how many times each line of code was executed, or highlights in this orange color lines of code that were never executed at all. So you can use this to see how well your test routines are covering your code, and if they're not covering it as well as you would like, you can see where you need to make improvements to get more coverage. Now, I'll mention, just because you have code coverage doesn't mean you necessarily have excellent testing, because you may not be hitting corner cases or other interesting values. You may not be using everything in a strenuous way. But certainly if you aren't executing lines of code at all, you're not testing them very effectively. So this at least gives you a leg up. So embedded Gcov, I'm working now on getting JPL permission to release this as open source code, which would be on the ordinary public github.com/nasa-jpl/embedded-gcov. So hopefully by the time you're reading this, that code will be there. You can go there, download it to your system, look at the comments in the header files, and begin customizing. I do also include with it a small example that you can compile and run on a Linux system. So you can use that to get a little idea of how this works. Also, I'll give a plug. You can see other JPL open source releases under the github.com/nasa-jpl umbrella. So if you're interested in seeing what other things people at JPL have been able to release as open source, you can look around there and see if there's anything interesting to you. So that's the end of my main presentation. Hopefully you found it interesting and think this will be a useful tool for you. I've got a couple of backup slides about some details that I mentioned earlier but skimmed over, so I'll talk about those for a couple of minutes. One is the support for the Gcov call constructors function, which you need if your internal system startup code doesn't call constructors, which Linux systems ordinarily automatically do. Embedded systems might not, especially if you're using plain C. So if you need this to happen, then you can uncomment in gcov public.h that I provide the gcov opt to provide call constructors to allow this function to be built into your system. And then you need in your linker file to provide a constructors section that defines these symbols that the Gcov call constructors function will use in order to loop through and call the constructor functions that GCC provided to initialize the coverage counter data. And then when you've done executing and gotten your data, to post-process it and split up the concatenated.gcda data file or data serial port log into separate individual files to process further with Gcov or other tools. This is the shell script on the left that I use to basically get rid of non-ASCII characters, convert it from a DOS file in my system to Linux. You may or may not need those things. But then call the awk script to do the splitting up into separate files, move those files to the object directory from Icode, and then reverse hexdump those files into the GCDA data file binary format. And this awk script on the right that splits the concatenation up, basically it just looks for each GCDA line, reads the file name from that line, creates a new XXD file to store the hexdump data, stores the hexdump data, and then on to the next file. So that splits it up into a bunch of separate XXD files, and then this can reverse XXD then to get the GCDA separate data files. And once you have those, you go on and process them as needed. So that's the end of my talk. Hopefully you've, again, found it interesting and will find it useful, please feel free to go to the github.com/nasa.jpl, NASA-JPL, sorry, and look around there for anything you find interesting, including embedded-Gcov, which again, hopefully by the time you're reading this, it will be posted up there. If not, please get in touch with me, ken.peters@jpl.nasa.gov, or try again at the GitHub later in the hopes that it has been posted. Thank you, and that is all.